Hello, everyone. I'm Brian Cairns.
I'm Cheryl Simon.
And we're going to tell you a little bit about the secrets behind the Drive Realtime API. So what does that mean? Well, first, we're going to give you a brief introduction to the Realtime API and a demo of what sort of apps you can build with the Realtime API. We're then going to go into a little bit more depth on the technical details behind Google's real-time collaborative technology, which is used in a lot of our products, as well as the Realtime API. We're going to talk through a few points about how you can design a good data model and avoid some of the potential pitfalls that come from collaboration. And then finally, we're going to give you a little sneak preview of things we're working on to improve the Realtime API for your great apps. So Cheryl, want to talk a little bit about the Realtime API? Sure.
So at this point, you guys are probably wondering, what is the Realtime API? So I assume many of you have used Google Docs before, or at least seen it. So what the Realtime API does is it allows you to take your application and add to it the power of instant collaboration, just like what you get in Google Docs. It's all done client-side via JavaScript API, so you don't even have to run your own server. But you get really powerful collaboration with click-by-click or character-by-character view of what your collaborators are doing. We handle conflict resolution, so if multiple people are making changes to the document at the same time or to whatever your application is. And you can get collaborator presence, so you can see who else is working on the document or playing the game at the same time. And this is all backed by Google Drive, which means that you get the power of Google's cloud storage services and high availability and all the sort of ecosystem that comes with Google Drive. So now we're going to show a quick demo just so you can just see. So the Google Docs you're familiar with are probably the docs, sheets, and slides that are more productivity focused. But so we just thought we'd show a quick demo of the other sort of things you can do with the Realtime API. So this is a little game called Realtime Cube that was written by one of our Drive developers, Mike Rocopio. And you can see here that as Brian makes a change to the cube, that change is instantly seen by all of the other players in the game. In the upper right, you can see the other people that are playing right now. And because this is backed by Google Drive, everything is stored instantly. So if you were to close and reopen the game, you could easily restore state. So let's just think for a second. What would it take to build this kind of collaboration system from scratch?
Ooh, I can do that.
Oh, yeah?
OK.
You think so? All right, well, let's think about it. So first, you need some sort of consistent storage, someplace that all these bits that represent the document are going to be.
Well, that's simple. We'll just throw it in a database.
OK. Well, what about authentication? How are you going to know who your users are?
I'm sure we can do something with like a cookie or maybe a session ID, something like that.
All right. What about your client-server protocol? What sort of networking are you going to have set up?
We'll use like JSON and come up with some sort of serialization format.
OK. How are you going to handle conflicts? What happens when multiple people are making changes together at the same time?
Well, we'll just tell our users not to do that.
OK. How about push notifications? You at least have to be able to tell the client when there's new changes available.
Well, if we just continuously make GET requests to the server, that pretty much solves itself.
All right. Well, what about document management? Or here's a good one, server failover. What do you do if your server crashes?
So there's only going to be one server. So if it crashes, then we'll reboot it.
OK. Are you going to handle undo redo?
To be determined.
OK. Well, what about authorization? This is really important. You don't want users to be able to see each other's documents or get access to things that they shouldn't have.
I can't really come up with anything for that.
Yeah, all right. Well, what about server affinity or data replication or user presence? Or how about sharing? Or document metadata, profiles?
I think this might be a little bit harder than I was thinking. What if there were some kind of an API that did all of this for us?
Well, luckily there is. So with the Realtime API, you can let us handle all of the complication of network communication, storage, sharing, high availability. All of that is handled for you. All you have to do is to create a real-time data model that makes sense for your application. So you can focus all your energies on just creating really awesome applications that'll make users really happy. So what's this data model look like? Thinking back to that demo we showed just a few minutes earlier, this is a representation of what this data model could look like. So at the root of the data model is always a collaborative map, which just is where you put all of the data objects that you need for your application. In this case, there's just a single collaborator list that consists of the moves that the players have made in the game. And each move is just represented as a JSON object. So these collaborative types, this map and list, are special in that whenever you add something or make a change to this map or to this list, the changes are automatically sent to the server and sent to all the different collaborators. So here, I'm going to show you in one slide all the code that you need in order to integrate the real-time API with this data model I just talked about. So the first thing that you do is you just load a file. And when you load it, you have to give it three things. You have to give it the file that you want to be loaded. And then you give it two function pointers. One that represents the file, what you want to happen when the file is loaded, and one that represents what you want to happen the first time the data model is initialized. So let's look at that second one first. So this initialized model is called exactly once for each time that the data model comes into existence. So not every time the document is loaded, just the first time the document is created. And here you want to initialize all the state that you want to guarantee that every document in your system is going to have. So here we tell the model to create a list, and that creates a collaborative list. And then we add it to the root by just saying, set this thing on the root with the name of moves. Then on the on-file loaded, this is what happens every time a collaborator opens the document. So what you want to do here is to set up some listeners so that you can be informed of when changes happen to this list. So in this case, we're adding an event listener onto that moves object that we created above, and we're going to get notified whenever a value is added to the list, and we just want to update the display when that happens. And then finally, you just need a little bit of code to respond to user actions. So whenever a user makes a move here, we'll tie this add move handler into it. So we create a new move, which is just a JSON object, and we add it to this moves collaborative list that we created before. And that's it. With just these three simple steps, all those moves are going to be automatically sent around, and you can update the display and handle all of the sort of complexity of networking storage. All of that is handled with just these three simple functions. And now Brian here is going to tell us a little bit about some apps that have already put this to use.
Thanks, Cheryl. So we have a lot of great partners that made really awesome apps for the Realtime API. We already demonstrated Realtime Cube, which was developed by a member of the Drive team here at Google. We also have some other apps that were developed by Google engineers. Multi-Sudoku was actually developed by Cheryl. It's just a Sudoku game, and it's really fun to play. And then we have another developer, John Day Richter, who developed a make-your-own adventure text-based game called CollabQuest, which is really cool if you're into MUDs or something like that. But maybe you're interested in something that's a little bit more productive than that. If you like editing code, and who doesn't, we have a great cloud-based IDE developed by one of our partners called Neutron Drive. Many of you have maybe seen this or used it. With the Realtime API, now you can collaborate on the code you have stored in Google Drive, just like you could collaborate on a document in Google Drive. And this is really great for like pair programming or code reviews or whatever you want to do to collaborate on code. If you want to plan some sort of project or a schedule, one of our partners created an app called Ganter. Ganter is a Gantt plotting program for project management and schedules and things like that. And now, of course, that's a collaborative activity, and you can now see people's changes in real time as they make them. Or if you're into doing some sort of diagramming, Draw.io has really great diagramming tools. You can make flow charts or network diagrams or any kind of diagram that you would want to make. And again, because of the Realtime API, now you can do this in real time, collaborating with other users. So lots of really great capabilities that the Realtime API can bring to your apps. And it's not just limited to productivity apps. It could work in games or whatever else you can dream of that you want to have real-time collaboration. So let's go through a few of the secrets of real-time collaboration. How does this technology actually work? So what's the goal with real-time collaboration? Well, the goal is something like this. This experience where everyone can edit at the same time and everyone can see everyone's changes in real time. But getting there is not actually as easy as it maybe seems, because we really want two properties out of this system. We want to be able to apply the changes to the data model immediately without waiting for network latency. Maybe you're on a crappy hotel internet connection, or maybe you're on the conference network here at Google I/O, And it takes 500, 600, 700 milliseconds for things to go to the server and back. You can't wait that long to update the local display. But then that means that every user is seeing a slightly different sequence of events in the document. And we need to come up with a consistent answer at the end where everyone gets the same result, regardless of the order or timing in which these changes were applied. And the way we do that is we break every change you do to the data model, we break down into these things called mutations. And a mutation is just a simple operation on the data model. So let's go through an example here. Here we have just a string, and we can assume this is a collaborative string. And the user starts with this string hello world, and they start typing in. Well, we generate an insert mutation. Let's say that the user inserted the word real time between hello and world. Well, we generate this insert mutation that says, insert at position 6, this text real time. When that gets applied, we end up with hello real time world, as you would expect. Then the user might decide, OK, I want to actually delete something. Maybe I want to delete the word world. So again, starting with hello real time world, the user goes and selects world and backspaces or whatever. And we generate a delete mutation that says to delete, starting in index 14, which is where the word world begins, these 6 characters. And of course, once that's applied, we erase that word world, and you end up with hello real time. What this means for storage is actually really interesting. So one way you could store this document is you could try to store a snapshot of the document or some sort of serialized form of the state. What we do is actually a little bit simpler and more powerful. We store the entire history of mutations that are applied to the document. So as you edit, every edit gets just stored in a log. And this is append only. And that means that we have the complete history of every state the document has ever been in throughout editing time. The one challenge this creates is that this log is going to get really, really long. And we don't want to send the entire mutation history every time you load the document. So what we do is we have a thing that takes a snapshot of the mutation log. It basically rebuilds the data model from this log and then creates a new set of mutations that is the minimal set of mutations needed to recreate the data model. So in this case, we have an insert, another insert, and a delete, and all of that gets condensed down into a single insert that recreates the final result. And that's what we send when we load. As I said before, local mutations get applied immediately. So in this case, we have 2 different users, Alice and Bob, who are both collaborating on this single string. If Alice inserts the word rainy and Bob inserts the word brightly at the same time, we apply both of those changes immediately locally. So you can see that Alice gets the rainy day dawned immediately, and Bob gets the day dawned brightly immediately. And this is great, but it's not collaborative. So what you might think is, why don't we just broadcast these mutations around and then apply them when we get them? And that sounds good, but the problem is that the mutations end up getting out of date. And let's go through an example for how this happens. So let's look just at Alice's state. Alice starts with the day dawned. She applies the insert of rainy, which she sent, and she also applies Bob's insert of the word brightly. The problem is you don't get the right result. Bob's insert is too far to the left in the string. The index doesn't make any sense because there was an insert that occurred before it. And you end up inserting in the middle of a word and nothing works. And that's the key takeaway here, is that applying mutations as is just doesn't work. What we really want to do is take these same mutations, but instead of applying Bob's mutation directly, we somehow fix Bob's mutation to shift it over to where it should have been and apply that. And when we do this, we get the correct result. Again, the key premise here is Alice needs to apply something that's been modified, not the exact same mutation that Bob applied. And the way we do this is through a process we call transformation. So let's go through an example of how transformation actually works. Again, we have Alice and Bob. They both send out their changes. Alice has the insert of the word rainy, Bob has the insert of the word brightly. And they both apply those immediately locally. They both then send those to the server. Let's say that Alice's gets to Google first. OK. The server looks at this, sees that there's nothing that Bob has yet sent to the server, so there's nothing we need to do. It just sends it over to Bob. and Bob gets the correct result. We're good. Bob now, his mutation that inserts the word brightly gets to Google. Well, Google, our servers notice that Alice's mutation came before Bob's mutation. And so Bob's mutation needs to be fixed to be in the correct location. And it looks at the indexes specifically here. It notices that the insert that Alice issued happened earlier in the document than the insert that Bob issued. And so it shifts over Bob's insert by the length of what Alice inserted. And this new transform mutation, which is now an insert at position 20, is what Alice actually gets. Alice applies it, and everyone's happy again. Yay, we win. But it turns out that's not really enough. Transforming on just the server doesn't actually solve the problem. And the reason is that the server doesn't know about every change, possibly until it's too late. So let's go through another example of where this might happen. Again, we have Alice and Bob both issue the same mutations they did last time at the same time. But this time, Bob's mutation gets to the server first. Well, the server doesn't transform Bob's mutation because there's nothing previous to transform it against. So the server just sends it on to Alice, and of course, panic ensues, and Alice is going to get the wrong result. Alice now sends her mutation, and let's say it gets to the server after Bob's mutation got to the server. Well, the server is going to transform it against Bob's mutation because it knows about Bob's mutation now. But Bob's mutation comes later in the document than Alice's mutation. So in reality, the transformation for this doesn't do anything. The mutation just gets sent as is over to Bob. And of course, the server gets the correct result, and Bob gets the correct result, but Alice didn't. So how do we solve this? Well, the solution is to put the exact same transformation logic we use on the server on the client. So we have this thing called the transformation manager that runs in every single client. In JavaScript, it runs on the server in Java. And we have this mutation queue that we keep, which is basically the list of all mutations that a user has issued but haven't yet been acknowledged by the server. In this case, Alice's insert of the word rainy goes on this queue as soon as it's sent. Let's say the server sent out Bob's mutation unmodified. Well, this transformation manager on the client notices that Bob's mutation needs to be transformed because it was not made with respect to Alice's mutation. So we send all the mutations from the pending queue and the mutations from the server through this transformer function, which is the same as it is on the server, and we get the fixed result, and everything's fine now. And then the server just has to acknowledge mutations. The server, when it receives a mutation, it just sends back an acknowledgement that looks very much like the mutation, but it doesn't have to have the actual data. And the client just removes the mutation from the pending queue. And that's how we manage conflicts in the system. That's how we keep everyone on the same state, despite the fact that these mutations happen in different orders. So let's look at a use case, Cheryl, where you have to undo a user's change.
All right, thanks, Brian. So a lot of times in sort of productivity-focused apps, a user wants to be able to just hit a button and have his last change get undone. So it turns out that this is a little bit complicated in a collaborative environment because it's possible that since he made his last change, other users have actually made other changes to the document. Well, it turns out that the same transformation logic that Brian just talked about can actually help us solve this problem basically for free. So let's just think about what might happen here for a minute. So we start with this document, the day dawned, and the local user tries to insert brightly into it. So what we do is whenever the local user makes a change, we add a mutation to the undo stack. And what this mutation is the inverse of the original mutation, such that if you applied this inverse mutation, it would undo the original mutation. So in this case, the opposite of inserting brightly is to delete 9 characters. So now this undo stack consists of a set of mutations that'll sort of like reverse the changes that the local user has made. And then later on the document, somebody else went ahead and made some more changes. So if we just keep the undo stack like that, and then we try to go undo that user's last change, we pop this inverse mutation off the stack and go and apply it, we run into this same problem where this inverse mutation doesn't make sense anymore. It goes and deletes the wrong section of the document. So we can solve this. So what we do instead is we still store this inverse mutation on the undo stack, but in addition, we actually go ahead and store all of the collaborator mutations as they come in. So now this undo stack consists of a combination of inverse local mutations and collaborator mutations. Then when the user asks us to undo, what we do is we walk down the stack and pop off all the collaborator mutations until we find one that belongs to the local user. When that happens, we pull this local user's mutation off, and we transform it against all of the collaborator mutations that have happened since. So in this case, the delete gets transformed against this insert mutation, from which we know we need to shift the delete over by 4 characters. So we get out this transformed mutation, which, when we apply it to the model, undoes exactly what the user did before. So we've talked a little bit now about how all this stuff sort of works behind the scenes. It turns out you really don't have to know all that in order to be able to use the API. But it can come in handy a little bit as you're designing your data models to just have a little bit of an understanding of how these conflicts are handled so you can understand the implications of the choices you're making in your data model. So now we're just going to go through a few examples of data models in this event planning system so you can see some of the challenges that come up when you're working in a collaborative system. So in this event planning system, you have a bunch of tasks, each represented by one of these blue cards. And each task has some properties associated with it, like what the task is that has to happen and how much time it's going to take. And then it's organized into columns, where each column is the work assigned to a particular user. So here's an example of what this data model might look like. You could have a collaborative map of users, each of which contains a collaborative list for each user, which in turn contains the specific tasks that are assigned to them. And so one situation that might come up is, here we have 2 properties, time and unit, that are sort of intrinsically tied together. It doesn't really make sense to update one of these properties without also updating the other one, or at least they should go together. So how would you handle updating these 2 properties atomically? Well, so this task is represented by something called a custom object, which is basically just a fancy way of being able to assign names to specific collaborative fields. So that means that when you change the values on these fields, what you end up with are 2 set mutations, one for the unit and one for the time. And this is all great as long as only one person is making a change at the same time, because you set the 2 properties and you're happy. But the problem comes in when somebody else comes in and makes a change at the same time. And the problem is that you can't control the order in which these changes happen. It's left up to sort of the vagaries of the network communication. So it's possible that half of Selena's change is actually going to come before Amir's change, and the other half comes after. And so the result of this is going to be that you have a task that has the time from what Selena tried to set it to, but the units from what Amir tried to set it to. And this is obviously wrong. You just don't want these 2 changes to be intermixing like this. So what do? We solved this with a concept called compound operations. So what a compound operation is a way to tell us that these mutations belong to a set and should be applied together at the same time. So all you do to create a compound operation is tell the model your beginning one, and then you go and make a bunch of changes to your data model, like setting the units or the time, and then you end the compound operation. And what happens now is the mutations that resulted in all the changes you made inside that block get sent over the network together as a set, and you can guarantee that they'll always be processed in order with nothing else being processed in between. So now we know that Amir's change is always going to be processed fully before we process anything from Selena's change. And so now we can guarantee that the end task is going to be in a consistent state. Now Brian's going to work through a different example.
Thanks, Cheryl. So here's another use case that you might see in this system. Let's say you have some priority assigned to these tasks. In this case, we have high, medium, and low. But you might have a real numbered priority or something like that. And you wanted to keep them sorted in some sort of priority order, where high tasks appear first in the UI, and then medium, and then low. Well, you might think the best way to do this is to just sort the data model. But the problem is that any sort you do in this system is going to be represented to the server and to every other collaborator as a series of inserts and deletes. And there's nothing stopping anyone from interleaving other inserts or deletes in between these changes, or for that matter, 2 people trying to sort at the same time. And the system has no knowledge the Realtime API has no knowledge that you wanted this to be sorted, and as a result, it has no way to know that these changes are somehow interrelated in very complex ways. And the result you end up with is that the sorted list is not necessarily going to stay sorted. In this case, we have an insert of a high priority task first, and then an insert of a medium priority task. And of course, because of the way indexes work, the medium priority task will end up first in the list, which is not what you want. So the solution to this kind of problem, and this is actually a generic solution that works with all kinds of different problems you end up with in the Realtime API, and it's very powerful, is to keep your data model unsorted and then do a sort, but only keep a sorted view of the data model. So this sorted view is something that's just local to your client and in memory. And you might think that this is very inefficient. I mean, after all, sorting is not necessarily the cheapest operation, and you might be doing it a lot. But the reality is, you can be a little bit lazier than that. As it turns out, you can sort just when the user loads the document, and then you add listeners to the unsorted view, and as users insert or delete items from the unsorted view or move them around, all you have to do is a simple binary search on your view to figure out what's the location of those items. And this sort of keep a modified view and then update it based on listeners is a very powerful technique that can solve a wide variety of problems. So let's look at another task.
All right, so another situation that you want to be able to do in this application is to assign tasks to different users. So you can do this just by dragging something from one column into another. So this is a little bit problematic, again, in a collaborative environment because this move is not an atomic operation. The move is actually going to be represented by two different mutations, a delete and an insert. And so, again, if two people make changes at the same time, you end up with problems. In this case, you end up with having the task in two different users' queues, which is obviously not what you were looking for. So what do we do about this? Well, one thing you might think is the solution, because it was a solution to a kind of similar problem before, is compound operations. But it turns out that this doesn't solve this particular problem. And the reason is that all a compound operation does is affect the order in which the mutations are applied, but it doesn't affect how the mutations are transformed. So in this case, we get these two compound operations, and we still individually transform every mutation within them against every other mutation, and then apply them individually. So the first transformation is a no-op, because we'll just assume we don't have any historical state. But then the second one is we're going to start with this delete here and transform it against the delete and the insert that came before. Here, the delete actually just goes away because the delete already happened, so it gets transformed to null. But the insert is actually the one that we want to go away, and it doesn't. Because if you transform the insert against the delete and the insert and the delete that came before it, nothing happens. They're all affecting different lists, so it doesn't really affect the ability for us to do this insert, so it happens anyways. So you still end up with the case where you have the thing inserted into two different lists. So what you want to do instead is to adjust your data model to make it so that this assignment is actually an atomic operation. So before, we had a list for every individual user, which represented the tasks that belong to the user. What we could do instead is just have a single list of tasks and make the assignee just a field on the task object. And because it's a field in a custom object, it just becomes a set operation. And if you transform two set operations against each other, one of them is always going to win. So you guarantee that you'll always have exactly one assignee for the card, which is what you were looking for. So up till now, we've been talking about things that you can do in the API today. So now Brian's going to give us a little bit of a sneak peek about what's coming up soon.
Thanks, Cheryl. So one thing that we've gotten a lot of feedback on, and we know that you value a lot, is the ability to get your data out of the Realtime API. And there's a lot of reasons you might want to do this. You might want to back up your data, or you might want to do processing of the data in the Realtime API on your server. And we want to make that possible. So we're excited to announce that we're going to be adding the capability to the Drive API to take a real-time data model and export a JSON representation of that data model. Now, because this is part of the Drive API, you can use any of the great client libraries we have for the Drive API for a variety of languages, or if you want, you can just use a very simple HTTP RESTful call to download this data model. And again, we use OAuth 2.0 for this. It's very simple to get set up. And you get this what the user does, the document, or whatever app you're building, we always generate a consistent format. And it's designed to be easy to understand from a human perspective and easy for you to work with in code. Well, of course, the natural follow-up to I can export the data is, what do I do with it once I get it out? And so we're also going to be adding the capability, again, to the Drive API, to take this exported representation and convert it back into a real-time data model. So let's say you have a JSON that has been exported, and maybe you've done some modifications to it. What you can do is you can upload it to the Drive API. Again, this is very simple using our client libraries or using a simple HTTP post call. We then take that uploaded representation and reconstitute a real-time data model. This is our sort of temporary model. And we take this temporary model along with the current data model as it exists on the server, and we run them through a diffing algorithm. And the diffing algorithm actually computes the mutations that take the current state that's on the server and transform it into the state that you uploaded. In this case, there's an insert and a delete. And again, these are just mutations, just like any other mutations in the system. And then what we do is we apply these mutations back to the data model on the server. And the net result of this is that if there were changes going on, they actually end up getting merged together. And if you have collaborators working on the document, they see the final result immediately. They don't have to reload or do anything like that. They see the changes in real time, just like they came from any other collaborator. And so we think this is a really great capability that you're all going to love and use in cool ways. But we also understand that you might want to have the full richness of the real-time API and programming model in different contexts. And of course, one of the obvious contexts is you want to develop a mobile app. So we're also excited to announce that we're working on an Android Java API for the real-time API. And so this will give you the same sort of great, easy-to-use objects, collaborative objects, and other capabilities as our JavaScript API, but in a Java environment. And I should say, we want this to work really well on Android, so we're doing a lot of work on things like keeping CPU usage low and making sure that we're not using a lot of bandwidth. But this is a generic Java API. So if you want to use it in a desktop Java application or you want to use it in a server-side Java application, that's great too, and it'll work wonderfully. And of course, because we have this sort of data model that we've built from the ground up, we can provide cross-platform compatibility. So the Java API and the JavaScript API work on the same data models, and we automatically translate between types for you. So if you have a collaborative string, for example, in JavaScript, you get the JavaScript object, the gapi.drive.realtime.collaborative string, which will have the properties and other things that you expect from a JavaScript implementation. If you take that same data model and load it with the Java API, what you'll get is another collaborative string, but written in Java. And the Java version will support the same interfaces that you expect from Java, things like appendable. So this makes it a great way to build cross-platform apps that share the same data.
So that's all we have for you today. I hope you guys learned a little bit about the Realtime API and how it can make it really easy for you to add collaboration to your own applications. And I hope you have a little bit better of an understanding of how it works behind the scenes, so this can help you design really good data models that'll make your applications just work really well. But now it's your turn. So we think we have a really great technology here that can enable some really amazing applications. But you guys are the ones with the great application ideas. So we just hope that you can go out there and put this to use. And we're really excited to see what you have going. So now we have time for a few questions here. And if you don't want to stick around, we'll be upstairs in the Chrome apps area later on this afternoon, so you can come find us.
So I was just curious about your implementation for that. Do you guys use WebSockets or long polling?
Yeah, so we use long GET requests.
Long polling.
And actually, so we use cores to do cross-origin communication, and sort of the design of the system is we want to be transport agnostic. So we use long gets because we want to have compatibility with older browsers, like we support Internet Explorer 9. But we haven't seen a huge advantage of going to WebSockets at this point. If that's something that is something we want, that'll be something that'll be transparent to your app. And again, on the Java API and all the other APIs, we we do are not necessarily going to use the same transport mechanism.
And then my other question was, so one of the things that you get with like Google Apps is the ability to have revision history. Right? Is that something that we have with this?
So we have not yet exposed the revision history for documents. It's something we're already keeping, and we don't have anything to announce right now, but that would definitely be a capability that would be really cool to have.
Okay, thanks.
Hi, John Blossom. It sounds like you've avoided certain things that were in Wave protocol, such as XMPP underpinnings and going to character-by-character updates and things of that sort.
So we can do a character-by-character updates.
You can, but if I understand from the examples, that's not what you're doing in terms of managing the stack of updates?
So an update could be a single character insert.
Right.
Or a single character delete. We have basically a throttling algorithm in place so that we batch up updates so that we're not using tons and tons of bandwidth for single characters.
So in effect, what you have is a micro timer, if you will. If somebody's a fast typer, then that's one update.
Right. So, and in fact, the algorithm is actually somewhat adaptive. So it tries to prioritize low latency if updates are coming slowly, and then it tries to prioritize bandwidth efficiency if updates are coming more quickly.
Makes sense. Thank you. On the JSON exporting of the data, you're exporting the data model, and as you said, it would be nice if you could export the history stack. Is there any provision of being able to export access capabilities for a federated model?
So we don't have anything to announce right now on that. I would love to chat about that if you want to come to office hours, though.
Thanks.
Gentleman in the back.
Do you have a maximum number of subscribers or collaborators?
I think the maximum number is 50. Beyond that, the more collaborators you get, they end up in a read-only mode. So it's 50 actively editing collaborators at a time. So
you can have anonymous collaborators that don't collaborate, they're kind of read-only, so could you use it kind of like as a pub-sub kind of thing?
We're probably not the best thing to use as a pub-sub kind of thing, but I mean, yeah, that's certainly a use case that you might consider if you like other properties of the API.
Okay. How would you represent something like a Google Docs, which has on one hand like a large body of text, and on the other hand, like the possibility to modify like individual characters and attributes? So what kind of data model would you use for that?
Well, so you're asking what kind of data model you would use to represent like a Google document?
Yes. Yes, formatting.
Oh, the formatting. So, okay, well, obviously the string is pretty easy. We have a collaborative string, which we didn't really talk about here, but which automatically handles all the like updates and edits to the string. We also have this thing called index references, which is a way for you to sort of put a pointer at a location in the string, and it'll automatically shift around with the updates. And so that's, we actually historically had a version of this working with these index references, where basically you can mark like the beginning and end of formatting areas in order to, and then you can apply that at the rendering phase.
And let's try to take a question, if we can, from...
Oh, yeah, is that actually... Yeah. While he's setting that up, you want to go ahead?
Sure, yeah. How do you handle authorization in the data model in terms of like segmentation of what certain users or certain roles can have access to edit or not access?
Yeah, so the real-time docs are just Google Documents, or in Google Drive. So we use their sharing and authorization services. So you can have viewers and editors, and you can actually integrate with the common sharing dialog in order to have that all be configured.
So that's at the document level,
right?
The
So
entire document?
the unit of access control is at the document level, and that each one will have a document ID. And you can manipulate these with Drive API if you want to do permissions or whatever. You can have multiple documents open at the same time. So if you want to have, in a single application, you want to have different parts that have different access rules, that's definitely something you can do. And in fact, something like Neutron Drive does exactly that.
Is that multiplexed over the same connection then?
So right now, we do not have connection multiplexing. There's a separate browser channel for each one of those.
Okay, thanks.
Is it possible to use the Realtime API for an offline sync, so two users make changes independently offline and then want to sync them?
So we don't currently have offline capability, except I should note the import-export capability is actually a pretty decent way to do offline. I think we're a little bit out of time, but I would be happy to talk about different ways you can implement offline if you'd like to come to office hours. And I should say office hours is immediately right now after this talk upstairs in the Chrome section over by the question booth. Thank you all.
Thanks.